Good afternoon, everybody, and welcome to Cyrsiau Carlam Cymru. Welcome to the fourth and final geography session, led again this evening by Ms. Delor Davies.
Hello and welcome to the fourth session, which is on Unit 3, the carbon cycle. My name is Ms. Delor Davies, and today we will look at the following topics: carbon cycle flows and stores, atmospheric carbon pathways and processes, ocean carbon pathways and processes, terrestrial pathways and processes, and equilibrium, feedback and thresholds. First up, we are going to look at 3.1.6, carbon inputs, outputs, stores and flows. So carbon is found everywhere. Thanks to its ability to bind with other elements, it has become the building block for life on Earth. Carbon-based molecules are integral to all living creatures. We've got carbon in ourselves. Wood is 50% carbon. Carbon dioxide and methane, another atmospheric gas containing carbon, are parts of the air we breathe. Carbon exists in a dissolved form in water and is present in limestone, fossil fuels, ocean sediments and soils. And carbon has become important politically too, because of the role CO2 play in anthropogenic man-made climate change. So the carbon cycle. The carbon cycle is a biochemical cycle by which carbon moves from one part of the global system to another. At the global scale, it is a closed system made up of linked inputs, outputs, flows and stores. At the local scale, it is an open system. So 3.1.1 to 3.1.5 was the water cycle, and 3.6 onward is the carbon cycle. So what is the similarity? What are the similarities between the carbon and water cycle? Well, both are natural systems. Both are inputs, stores, flows and outputs. Natural changes can occur to both. Human or anthropogenic changes can occur to both. So here we have on the screen now the components that make up the carbon cycle. So the cycle has a store, and the stores are the amount of carbon held by the global system. For example, the atmosphere, oceans and biosphere. It has flows. So flows are movements or transfers of carbon between stores. For example, volcanic activity adds 0.1 gigatons of carbon to the atmosphere annually. Inputs, they are flows into stores. For example, carbon dioxide added to the atmosphere by human activities. And the cycle has outputs, so flows leaving the stores. For example, dissolved carbon carried from the land in solution by rivers. This slide here shows the global cycle in a diagrammatic form. The squares on the diagram are carbon stores. The carbon flows that goes through these stores are driven by a range of natural processes we'll look at later on. In brackets in each box, we have a number in a bracket, and this shows the amount of carbon in gigaton, and 1 gigaton is 1 billion tons, and it is shown like this on the screen on the left here, GTC, gigaton carbon. Okay, and that's the most common unit in this unit of work, okay, when we're looking at the global cycle. So okay, in red in the carbon cycle diagram, we have the residence time. The residence time of carbon is the average length of time it remains in any carbon store. The amount of carbon held in each store is subject to is subject to change over timescales ranging from a few minutes to millions of years. These changes are known as fluxes. As you can see in this diagram here on the screen, the residence time of the carbon is at its longest locked away in sedimentary rocks and fossil fuels at 150 million years. Before weathering and volcanic activity eventually released the carbon. One of the Earth's largest carbon stores in the world currently are the Himalayas. These mountains are composed of oceanic sediments rich in calcium carbonate, and they were folded upwards long ago due to the convergent plate boundaries. So we have two plate boundaries converging together and folding upwards. And whilst falling upwards, you have a disappearing sea where you had a lot of marine animals and shells, and that's turned into calcium carbonate. And the carbon on the Himalayas are actively weathered, eroded, and transported back into the oceans. And another factor that plays a big role in this shift is monsoon rainfall and runoff, which transports the calcium carbonate into the oceans. So as you can see there, sedimentary rocks and fossil fuels are the largest store of carbon, but also it keeps on to the carbon for the longest period of time. Okay. Here we have a table showing the global carbon stores. They are naturally occurring volumes, and on the screen here, they do not take into consideration human or anthropogenic activity. So as you can see here, by far the largest carbon store in gigatons are sedimentary and deep ocean sediments, 100 million gigatons. Second, we can see ocean water, both in biomass and dissolved CO2, which is 38,700 gigatons. And the least there is the biosphere, which are forests and grasslands with only 560 gigatons. If you are being assessed this up and coming few months in physical geography, and you have an essay on the carbon cycle, please make sure that you do use data to support an overview of the various global carbon store. For instance, the atmosphere naturally contains 600 billion tons of 600 gigatons of carbon, but as a result of human activity, for example, burning fossil fuels, deforestation, this figure has actually increased to more than 800 gigatons. Okay, so I want you to quantify when you are talking about different carbon stores and different pathways, etc. Okay. The concept of mass balance can be applied to the carbon cycle. This means at a global scale, the total amount of carbon is conserved over time. So maintaining a steady amount of CO2 in the atmosphere helps maintain stable average temperatures at a global scale. However, because fossil fuel combustion and deforestation have increased CO2 inputs into the atmosphere without matching increases in the natural sinks that draw CO2 out of the atmosphere, these activities have caused the size of the atmospheric carbon pool to increase. So as good geographers now, you will quantify that. You will say usually the carbon storage of the atmosphere will be 600 gigatons, but due to fossil fuel combustion and deforestation, this has increased to 800 gigatons. Okay, so unfortunately, the outputs are bigger than inputs in the carbon cycle due to anthropogenic activity, and this has therefore had an impact on global warming. Okay, now we're going to look at carbon pathways. Simply put, how is carbon exchanged from one store to another store. For example, from land terrestrial to atmospheric store. Scale is another concept in geography, and you must know that carbon pathways can occur at either fast, short-term and local scale, often referred to as a fast carbon cycle, or the slow carbon cycle, where carbon is exchanged over very long timescales of millions of years and often on a huge continental scale. And that's a slow carbon cycle. I'll go into it in more detail in a minute now. But another concept in geography is scale, and you can discuss the pathways and the carbon stores, but you can differentiate between local scale and continental scale, or fast or slow scale. Okay. Oh, sorry. Another really important term in the carbon cycle is carbon sequestration. So carbon sequestration is the term used to describe the transfer of carbon from the atmosphere to plants, soil, oceans and rock formations. Carbon sequestration is both a human and natural process. Carbon capture is a term used to describe the use of technology capturing carbon emitted from power station. We haven't really looked at that that's not really in the spec, but carbon sequestration is. So when carbon is put into long-term storage, okay? Now, firstly, we will look at how carbon is exchanged between the atmosphere and the land. Vegetation plays an extremely important role here. You would have learned this firstly in GCSE Science and GCSE Geography prior to A-level, and the role vegetation plays in carbon sequestration. Okay, and here we have just a quick overview on the screen now of the processes that the vegetation and trees, for example, do with sequestering carbon and also emitting carbon to the atmosphere. Okay, so first up is photosynthesis. This is one pathway between land and the atmosphere, and or the atmosphere to land. So photosynthesis is a process used by land plants and marine phytoplankton that convert light energy into chemical energy that can later be released to fuel the organism's activities. This chemical energy is stored in carbohydrate molecules, such as sugars, which are manufactured from CO2 and water. So glucose is used as a building block of cell walls in the form of cellulose, which is an important carbon store, for respiration inside plant cells, which provides energy for the plant, and to be converted into fats and oils, which act as an energy store. So photosynthesis removes carbon from the atmosphere, and carbon is now stored within the plant. Okay. Another important term is this NPP, the net primary productivity. The NPP is a measure. An NPP of an ecosystem is a measure of the rate at which new organic matter is produced by photosynthesis per unit area per unit time. The three global environments with the highest levels of NPP are, in order, shallow warm water estuaries. So they're warm water, so they're usually between the tropics, and by estuaries you will often see coral reefs, which we've done in year 12 if you've done coasts. Marshes are also a big store of NPP, and tropical rainforests. So these are all quite humid, warm places with thick vegetation. Okay, another pathway is respiration. Respiration is the reverse of photosynthesis. It releases energy by breaking sugars. CO2 is released into the atmosphere. Respiration and photosynthesis are elements of the fast carbon cycle. 1,000 times greater volume of carbon is exchanged than is through the slow carbon cycle. This is fast because it happens seasonally and year to year. But as you can see here, it happens a lot. The volume of it is also larger than the slow carbon cycle. We'll look at it a bit. Okay, another fast pathway is decomposition. So here, carbon is released as CO2 when living organisms dies and are decomposed by microorganisms such as fungi and bacteria. The temperature has a significant impact on the rate of decomposition. Humid environments such as the tropical rainforest have rapid rates, whereas colder environments such as Arctic tundra have slow rates of decomposition. I've got it here that decomposition in the Arctic tundra, you can see recognizable plant and animal remains that can lie on the surface for many months or even years before decomposing, whereas a leaf in the Amazon rainforest will take days to decompose. So there you can compare the rate of decomposition in terms of the climate. And now that will hit AO2 because, again, you're looking at other factors and you're applying knowledge in the fast carbon cycle. Okay, burial and compaction. Burial and compaction is where organic matter is buried by sediments and becomes compacted. Over millions of years, this organic sediments containing carbon may form hydrocarbons such as coal and oil, fossil fuels. Shelled organisms and coral absorbed carbon dioxide from the water and converts it into calcium carbonate, which builds their shells. When these organisms die, they sink and they accumulate on the seabed. Carbon dioxide is released as the carbonates dissolve. The remainder becomes compacted, forming sedimentary limestone, which stores carbon for millions of years. Okay, so as you can see on the diagram there, shells sink to the bottom of the sea. They come compacted, turn into sedimentary rock, which is limestone, and that's a large store of carbon. Okay, here we have combustion. This is a fast pathway. When organic matter burns, combustion occurs. This causes carbon to be released as CO2. Combustion happens naturally by wildfires caused by lightning strikes. This leads to increased nutrient and carbon recycling and results in growth being stimulated. This is essential to a number of ecosystems, including grasslands in East Africa. I live in Pembrokeshire, and at the moment the farmers are setting bits of the Preseli Mountains on fire because by setting bits on fire and getting rid of the old, overgrown, harsh shrub that the sheep can't graze on, it enables new fresh grass to grow. And it's important then for grazing on the Preseli Mountains. Okay, human activities cause a significant amount of combustion. So this is now human combustion. Lightning strikes, forest fires by lightning strikes are physical, natural. So human activities cause a significant amount of combustion. Burning fossil fuels such as coal, oil and gas results in stored carbon being released in carbon dioxide. This leads to a net increase in CO2 in the atmosphere. Burning biomass fuel is regarded as being carbon neutral because new crops have been planted and absorbing carbon dioxide from the atmosphere when plant-based materials are burnt. As long as the system is sustainably managed, there is no net increase in carbon dioxide. Okay, So now we're going to look at the carbon pathways between the oceans and the atmosphere. The oceans take up carbon dioxide by carbon cycle pump mechanisms. The carbon cycle pump processes operate in oceans to circulate and store carbon. So there are two carbon cycle pumps. The first one is biological, and the second one on the screen there is physical. So firstly, we're going to look at the physical or inorganic pump. Inorganic because it's not living. Okay, the physical or inorganic pump involves the movement of carbon dioxide from the atmosphere to the ocean by a process called diffusion. Have you ever gone to bed at night with a glass of water on your bedside cabinet, and when you wake up in the morning, your glass of water is full of bubbles? Well, that's because carbon dioxide from the air has diffused into the glass of water. And the same things happens with the ocean. So the upper layer carbon is diffused from the atmosphere into the upper levels of the oceans. Okay. Carbon dioxide is dissolved in the surface of the ocean and can be transferred to the deep ocean in areas where cold, dense surface water sinks. You know, that's a concept, something we've seen often in physical geography. When something is cold, it gets more denser, and it sinks. This downwelling carries carbon molecules to greater depths where they may remain for centuries. And carbon dioxide diffusion determines the acidity of the ocean. So here we have that diagram again on the right there. This diagram has both pumps on, but look at the right there. You can find the physical or inorganic pump where carbon dioxide is moved from the atmosphere to the ocean by the process of diffusion. And then carbon dioxide from the upper surface of the water is then transferred to the deep ocean where it is stored. Okay, so that's the physical inorganic pump. Now we're going to look at the biological pump. So this is a second pathway from ocean to atmosphere and back. The biological organic pump is driven by ocean phytoplankton absorbing carbon dioxide via photosynthesis. These organisms form the bottom of the marine food web and live in the ocean surface layer. Phytoplankton are consumed by other organisms and carbon is transferred along food chains. Organic carbon may eventually be transferred to the deep ocean when dead organisms sink towards the ocean floor. And that is the biological pump. Okay, now we're going to look at the carbon cycling between the land and the ocean. This is sometimes known as the slow carbon cycle, which I previously mentioned. Okay, cycling of carbon between the terrestrial, bedrock and oceans occur over millions of years through processes of weathering, erosion and deposition over very long timescales, millions of years, and at a continental scale. Remember what I said earlier about scales and how it's important and it hits the AO2, so please remember that. Rainwater containing weak carbonic acid reacts with limestone to produce soluble calcium bicarbonate. One example is where on the land now you've got where limestone and rain reacts with the limestone causing carbonation, which then releases carbon into the rivers, for example. Calcium bicarbonate moves through the water cycle in solution into rivers and the ocean. Next, calcium bicarbonate is used by marine organisms to create their shells. These are deposited later as carbonate-rich sediment on the ocean floor where they are lithified. They are turned into sedimentary rock. Okay, so I'm just gonna recap that. For example, now we've got on land we've got weathering occurring, where limestone reacts with minerals in rainwater, and that causes carbonation, which is types of chemical weathering. This releases carbon into, let's say, rivers, which would eventually reach the sea, the oceans, and then that carbon will be used in creating shells. And when those marine organisms die, shells sink to the bottom of the seafloor, they get compacted, lithified, which is turning into rock. Okay? Right. Oceanic crust containing sedimentary rock. Okay, we're now having our tectonic thinking hats on. So oceanic crust containing sedimentary rock, which is full of carbon, as we've just seen, okay, due to compressed marine organism shells, is subducted, causing the crust to melt and form magma. Okay, so for example, if we've got a convergent plate boundary, okay, this is revising year 12 now, okay, we've got convergent plate boundary. The oceanic plate is more dense and will always subduct, but as it subducts, it gets hot and it melts to form magma. But remember, we've just learned that the sedimentary rock, which, you know, the ocean crust, is full of carbon. So that now, carbon is now in the magma. So carbon dioxide that was stored in the rock is eventually released into the atmosphere through volcanic eruption. Now, this is something that takes millions and millions of years, okay, because it's such a slow process. And when the volcano erupts, that carbon is released back into the atmosphere, okay? Now, specialized concepts in geography, I've mentioned these at every presentation so far because I think they're extremely important, and every 21st century geographer needs to use them correctly in their essays. And here we have just a few random ones from the list. But ones that we've looked at today is system already, because the carbon cycle has inputs and outputs and stores and flows, so it's a system. We're going to look in a while now on equilibrium and feedback in the last 15 minutes of this presentation. Scale, well, we've mentioned scale. We've looked at local scale, for example, vegetation. We've looked at more continental scale, for example, subduction of the plates, you know, a slow carbon cycle. Interdependence, not really applicable in this unit. Mitigation, not quite. Causality, yeah, and threshold. We'll have a look now at equilibrium, feedback, and threshold in more detail, okay? Now, 3.1.10, which is feedback in and between the carbon and water cycle. I'm going to touch on this now, and we'll see how we can use these concepts correctly. Okay. Feedback loops. If natural systems maintain or lose a balanced state, this is known as a steady state equilibrium. Right, there's something called a positive feedback loop and a negative feedback loop. Please don't associate the word positive with good, happy, and negative as being bad, okay? They have very different meanings and they can sometimes get a bit confusing. Okay, so positive feedback loop. In a positive feedback loop, the output of the system serves to reinforce or amplify the initial disturbance. In this way, for example, A produces B, which creates more of A, which produces more B, which produces more A, which produces more B. So what you've got there is a system that's losing control of itself. Okay, that's a positive feedback loop. A negative feedback loop, the output of the system acts to restrict the effect of the initial disturbance. In this case, A produces B, which reduces the amount of A. As a result, equilibrium is restored. It's self-regulating. Now, another concept is threshold. So a system threshold or tipping point is a critical level that must not be exceeded if positive feedback loops are to be avoided, meaning the original equilibrium state cannot be restored. In studies of feedback, the concept of a system threshold is also important. Okay, we just mentioned it previously in the previous slide. I'm just going to say it again. This is a critical limit or level that must not be crossed if accelerated and potentially irreversible changes are to be avoided, making it much less easy for the previous equilibrium state, XOT, to be restored. For example, many scientists believe that a global temperature rise in excess of 2 degrees will lead to widespread and irreversible changes in the global carbon cycle because of positive feedback processes. You see that on the news. There's about climate tipping points. There's all over the internet interesting articles about this as well. At a local level, overgrazing of vegetation in an area at risk of desertification could cross a threshold. For example, if too much vegetation is lost, widespread soil erosion could follow. Once this happens, vegetation cannot easily recolonize. Irreversible loss of both vegetation and soil store means that local water and carbon cycles are permanently damaged. Okay. On the screen here now, we've got a map showing just some examples of positive feedback and places where the tipping points are very real, the risk is real. So remember, tipping points are threshold where a tiny change could push the system into a completely new state. Okay? So, for example, forest bug kill, forest fires, Amazon dieback, ocean warming, thawing permafrost, etc. Okay, human impact on the carbon cycle feedback loop. We are trapped in a positive feedback loop with our alteration of the carbon cycle through, burning fossil fuels, deforestation. Melting white ice in glaciers and ice caps have dark underneath, absorbing more light. Remember albedo? Apologies. A light surface has higher albedo and reflects the Earth's rays. Melting permafrost releases trapped CO2 and methane, which are greenhouse gases. Warmer oceans lead to more evaporation. And water vapor is a greenhouse gas. Warmer temperature can lead to drier forests, and more forest fires can release carbon dioxide and water vapor. All of these increase warming and causes themselves to speed up and creating a positive feedback loop. And also clouds have a role in this. So cloud type, sorry. So cumulus clouds can be negative feedback loop because they are very thick and white and fluffy and reflective, so higher albedo. And cirrus, they are more vapor and they behave as a greenhouse gas, so they accelerate warming. So that's an example of cryospheric positive feedback. Deforestation, means fewer trees, which means less evapotranspiration and less moisture entering the atmosphere. So here we have an example of the Amazon rainforest die-off. Okay. Look at the screen there for a second. Okay. Now, here we got a methane feedback loop. Methane is a powerful greenhouse gas, volumes of which are stored in frozen soil under the in the Earth's permafrost region. Around a quarter of the Earth's surface is either sporadic or continuous permafrost. These include the tundra, the polar and mountain regions, mostly in the northern hemisphere. Reports indicate that methane storing permafrost is now shrinking at an alarming rate. So the effect of permafrost melting are potentially magnified over time by positive feedback loops. So this is the step. So as the atmosphere warms, the permafrost melts and retreats to the higher latitudes. This will release methane that was trapped under the permafrost that's now melted. The atmosphere will warm up even quicker. Even more methane will be released by more melting permafrost, and this could quickly mean the Earth's climate will go beyond the tipping point threshold. This is a permafrost map, and as you can see, permafrost are found on land and both below the ocean floor. It is found in areas where temperatures are rarely above freezing. So it's widespread in Arctic regions of Siberia, Canada, Greenland, and in Alaska, 85% of the state is permafrost. This is an interesting article I found about permafrost melting. So how microbes in permafrost could trigger a massive carbon bomb. Okay, if you want to do extended reading, there's very interesting articles about it online. But what we are seeing now is methane are usually stored in wetlands, like we see here, for example, northern Russia. But due to permafrost melting and retreating to the higher latitudes, we are seeing more and more methane being released. Okay. Here we have terrestrial carbon feedback, which is another positive feedback model. So increasing water vapour in the atmosphere, because water vapour is also a greenhouse gas. This could then lead to further temperature rise, and then if temperature rise, then we've got permafrost melting and methane gets released. Also, as the temperatures increase, it reduces the ability of the ocean to absorb surplus CO2. Warmer oceans are less effective at absorbing carbon dioxide compared to colder water. Okay, so here we have marine carbon feedback loop. So I won't go in too much detail here, but ocean acidification could also impact on coral and marine ecosystems, and which can cause a positive feedback loop, okay, because less biological sequestration. I've got a bit of a time limit, so I can't go into that in much detail. Now, here we have a negative feedback cycle, which are a bit of an alternative. So feedback cycles are not always predictable. So here's an alternative scenario for the Arctic, which is the cryosphere. So ice melts to expose the darker coloured ocean, which absorbs more sunlight. As the ocean gets warmer, we've got increased levels of evaporation. This creates more cloud. This light-coloured cloud has high albedo and reflects incoming radiation, much as the ice used to be. As a result, less light reaches and is absorbed by the ocean surface, and then the temperature of the water falls. So that's an example of negative, okay, and how the system can self-regulate if the Arctic melts. Right, diolch yn fawr, thank you very much for tuning in for the past 4 weeks. Best of luck in your up-and-coming assessments. Please now to remember to use key terms and specialised geographical concepts in your writing. Please take extra care of the command words for each question, as your teacher will use assessment objectives to mark your work. Okay, so the two ones that you need to be aware of now for maybe if you've got an essay coming up is AO1 and AO2. AO1 is so assessment objective 1. You demonstrate knowledge and understanding of places, environments, concepts, processes, interactions at a variety of scales. And then AO2 is applying knowledge and understanding to interpret and analyse. Now, Please familiar yourself with the assessment objective breakdown marks for each question. For example, now, if you've got an 18 marker essay for carbon or water cycle, it is 10 marks for AO1, which is your knowledge and understanding, and 8 marks for AO2, which is application of knowledge. So please, when you're writing of it, think of 10 plus 8 and make sure that you try and use your concepts, use scale, and answer the command, answer the question, but also look at the command words carefully to see that you are hitting the marks that you can. I wish you all the very best in your upcoming assessments. Pob luck, and thank you very much. Diolch yn fawr. Hwyl.